Hello students, welcome back to Math 332 Elementary Linear Algebra. In this video, we are going to look at a new concept called orthogonal complements. All right, orthogonal complements of a subspace in Rn. So because these are the slightly more abstract concepts and this whole thing involves a lot of proofs. So I don't want to rush it. So I decided to make a two-part presentation for these topics. And this is the first part of the presentations. All right, so let's get right to it. All right, so let's first look at the objective for this video. So we are going to use this opportunity to introduce the concept of orthogonal complements, and we are going to develop some of these interesting properties and useful properties that we might not be able to use it today, but you are going to remember it, and we are going to use it at the end of the semester. So this video is kind of a little bit strange because we say a lot of stuff, but it doesn't seem to go somewhere, but it will at the end of the semester, okay? So for the objective, we are going to have to make sure that you know how to find the orthogonal complements of a subspace W, which is sitting in Rn. And you need to know some of the important and interesting properties for orthogonal complements, and you need to know how to state the fundamental theorem of linear algebra. Okay. So in the previous video, we talked about dot products, right? Dot products, and if you are given a vector v, all right, and let's say this is an element in Rn, and you're also given a vector u. Again, this is a vector in Rn. We know that if the dot product of these two vectors give you 0, okay, again, this is a number. Dot products of two vectors do not give you a vector, so give you numbers. So the dot product of these two vectors, if we give you the number 0, then we say that vector u and vector v and vector u, these are orthogonal vectors. They are orthogonal to each other. So if you are in R2 or R3, we can kind of represent it with this. I mean, in Rn, we do it the same thing too. It's just that it's actually very difficult to imagine what exactly happening in R10 or R20 or something like that. But you know what orthogonality means. Basically, these two vectors are perpendicular to each other, okay? Now, so right now, we want to talk about something a little bit different. So we have a vector v, and we want to talk about what does it mean for this vector v, which is in Rn, to be orthogonal, right? Is to be orthogonal not to a vectors, but to a vector space W, okay? So what does it mean for vectors to be orthogonal to a vector space W? For that, let's look at the definitions. All right, so let's look at this definition here. So we have Rn, okay? And we have a subspace W of Rn. All right, so these are all fixed and given. And what does it mean for a vector V that is in Rn that is orthogonal to this vector space W? Now, we say that this vector V is orthogonal to this vector space W if and only if this vector V, all right, is orthogonal to every vector that is from W. So we want this to be equal to 0 for all the W, that is in this vector space W. So imagine that we have an element here, all right? Then the dot products of V and this has to be 0, all right? If you have another element here in W, then this vector V and this element is actually orthogonal. You have another elements here, this vector V and this vector here has to be orthogonal. In fact, this vector V has to be orthogonal to every single element that is from this vector space W. If you can find such a vectors that is orthogonal to every single vectors that is in W, then V is said to be orthogonal to this vector space W, all right? So that's what I'm saying here. A vector V in Rn is said to be orthogonal to a space, okay? This is something that is new, okay? We haven't done it before. So a vector V in Rn is orthogonal to a vector space W if this vector V is orthogonal to every vector in W. All right, so let me ask you a very quick questions right here. Okay, so let's redraw this picture one more time. Let's redraw this picture one more time. So we have Rn, okay, and we have a vector subspace W of Rn. Now, according to this definition right here, can you think of an element that is orthogonal to this vector space W? So what I'm asking is, right? So what I'm asking is, can you think of a vector which is orthogonal to this vector space W? Think of one vectors that is the dot products with every single element that is from W will give you 0, right? What is that? Are you thinking the same as what I'm thinking? So there's one very, very special vector that has that property, right? That vector is the 0 vectors. 0 vectors dot every single vector that is from W is going to be 0. In fact, this vector doesn't even have to be in W. This is any vectors in Rn. So you have any vectors that is in Rn, you take the dot product with the 0 vectors, the answer is always going to be 0. So by definitions, this element here is orthogonal to this vector space W. Okay? All right, so what we're going to do next is we are going to take a box, all right, and we are going to pick up all the vectors that is orthogonal to this vector space W, all right? So we know that 0 is orthogonal to this vector space W, so we are going to put our vector 0 into this box. This is one of the obvious choice, right? They might be some of the vectors we don't really know, but suppose we do found a vector v such that v dot w is equal to 0 for all, okay, not just for one of them, but for all w in w, then this v here will be put into this box. So we are collecting, basically, we are collecting all the vectors that is orthogonal to this space, this vector space W. And we put them all into this box. So mathematically, we are putting them all in the set, right? So all in the set. So we are looking at this set, which consists of all the vector in Rn, such that the dot product with W is equal to 0. And key thing is here, not only one W in this space W, but for all, every single W that is in this set, you have to make sure that they are orthogonal to this vector v. If you found such a vector, put them all into this set, okay? This set is now called the orthogonal complements of this vector subspace, W. And it is denoted by this. This is how you write it. It's called W perp, P-E-R-P, which is a short for perpendicular. So this is known as W perp. So W perp is a set. It is called the orthogonal complements of this vector subspace W, and the definition is given precisely by this. All right, so given a vector space W, all right, which is sitting inside this Rn, we can actually construct a new set which is called W perp, which is basically a collection of all the vectors that is orthogonal to this vector space W. Okay, so now let's look at this example. Okay, so let's look at this example. So we have W right here is a span of one single vectors. That vectors is 2, -3, and 4. That's what it said. So geometrically speaking, we can kind of draw it because this is in R3. So geometrically speaking, W will looks like a line that passes through the origin. So W here, okay, is a collection of all the vector that is on this line, okay? That is on this line. This is going to be your X, Y, and Z. So this is W. So this W, as you can see, because it is a span of a vector, so it's definitely a vector space. This is something that you should know now. And so we wanted to find, okay, an orthogonal complement of this set W. So we wanted to compute what is the orthogonal complements, okay? So what is the orthogonal complement, all right, of this vector space W, okay? So this is known as W perp. So we are looking for all the vectors such that the dot products of every element that is from this set is going to be 0. Now, even though we have infinitely many elements that is in this vector space W, but because it is a span of these vectors, so one thing we know is that if you have a W, okay, so if you have vector W that is coming from this vector space W, this one right here, then your W is a linear combination of these vectors, which means your W is going to be C, okay, multiply 2, negative 3, 4, where the C here is a number. All right, so every element inside here can be written like this. So if you are looking for vectors V, okay, let's say this is a vector V, all right, such that it is the orthogonal to this, right, orthogonal to this vectors, then you have to make sure that their dot product has to be 0, okay? All right, so you want these equations to hold for all possible scalar, and you always want it to be 0. And this will actually implies that this dot product right here has to be 0. So what I'm saying is, if you do have a vector V, that is orthogonal to every single vector that is coming from this vector space, then that vector V with components x, y, z must satisfy these conditions. Okay, must satisfy these conditions. So these conditions, all right, the dot product of these two vectors has to be 0. So the dot products will give you 2x plus minus 3 and then y and then plus 4 times z has to be equal to 0. So W perp will consist of all the vector where their component x, y, and z has to satisfy this equation. All right, and we know that from Calc 3 or some our prior knowledge that an equation in R3 that looks like this, that is exactly a plane. So that is exactly a plane that passes through 0. So that's exactly the plane that passes through 0. So that is your W perp, right? So that is your W perp. And as an exercise, you can also work this out, and you will see that another way of writing W perp, instead of writing these plane equations, we can also write out the two vectors that span the entire plane. So these are the two vectors that span the entire plane. All right, so that's W perp, where your W, okay, where your W is a line that passes through the origin, all right, that passes through the origin, and that is your W. That's the span of the vectors 2, negative 3, 4. And again, another thing that you can relate to your Calc 3 is that this plane equations has a normal vectors, and that normal vector is 2, negative 3, 4. So this is not a big surprise that this normal vectors right here is going to be one of the elements of W, okay? So it's going to be one of the elements of W. They are orthogonal complements of each other. Does that make sense? Okay. All right. So this is one of the example for this W, okay? All right. Now, so I want you to try it this time on this particular questions right here. So now you have a vector space W. This time your vector space W is spanned by these two vectors. Let's call them W1 and let's call this W2. All right, this is basically your I and J vectors. So this is your basically I and J vectors. So you have your Z, you have X and Y. All right, so the span of your I and J is basically this is your XY plane. All right, so that is your W. And the question now is find W perp. All right, I will give you a couple of minutes to work on the problems, and you can pause the video, and when you are ready, you can restart the video, and I will come back and we can look at the solution together. All right, welcome back. So let's look at the solutions, and this solutions also illustrates one of the good observations that we can summarize it as a theorem, okay? So now we have W1, which is this vector, and W2, which is this vector. W is a span of that two vectors, and we want to find W perp. So W perp, by definitions, as you know, is, in this case, all the vectors, all right, all the vectors V in R3, such that V dot W is equal to 0 for all W in this vector space W. Okay, now, so this is actually a set, all right? It's a vector space, but it's also a set which consists infinitely many elements. There are infinitely many elements. So if you want to actually follow these definitions, this is going to be tricky because you will have to verify that the vector v, okay, the dot product of this vector v, and every single one of the w in w has to be 0. You have to find a vector that is orthogonal to every single vector that is coming from this vector space w. So this is difficult to do, in fact impossible. However, okay, even though we have w right here consists of infinitely many elements, but we know how w looks like, because w here is not any set. It is actually the span of all these two vectors. So we know that if you have a w that is from this vector space w, then this w must be in this form. It must be c1, okay, of w1 plus c2 of w2 for some kind of c1 and c2 which are real numbers. Okay, so if you select a vector that is from this set, now obviously you have to know by now that that particular element will have this form right here. Okay, now I am claiming that if you have a vector u in R3 such that the dot products of the u and w1 and the u and w2 is 0, then these vectors will definitely be orthogonal with vectors that looks like this. All right, this is pretty obvious actually. Let me say that again one more time. So I am saying if you can find a vector u that is in R3 with this property that I call property star, okay, if you can find a vector u in R3 with this property where the u and w1 they are orthogonal, u and w2f they are orthogonal, if you have that, then u, this vector u, must be orthogonal to a vector w that is written as c1 w1 and c2 w2. All right, so how do we see that? Now, easy. Let's do the dot product computations. So given we have this property star, then the u dot w, right, is going to be c1 of u dot w1 plus c2 of u dot w2, and because u dot w1 and u dot w2 is 0, how do you know that? Because of this property. So u dot w will also be 0. Okay, so if you have a u that satisfies these conditions, then u will be orthogonal to this w. This, by the way, is any w that is from this set. All right, that means what we have shown is that if you have a vector u in R3 with this property, then this vector u is going to be in w perp because it is going to be orthogonal with every single vector w from that vector space w, which is the span of w1 and w2. Okay, now let's look at the other way around, right? Let's look at the other way around. If you have a vector u, this time it's in w perp, that means u dot w will have to be equal to 0 for all the w in this vector space w. However, we do know that w1 is an element of w, so this requirement also implies that u dot w1 has to be 0, okay? Because this u here has to be orthogonal to every single vector that is in this vector space. w1 is in this vector space, therefore u must be also orthogonal to w1. And similar reasoning will give you u will also have to be orthogonal with w2. So what this shows is that if u is in w perp, then u must have this property that we label as property star. And if your u is satisfying this property star, then this u here will be in w perps. Okay, this u here will be in w perp. So this observation allow us to find w perp pretty easily if you know that your w is a span of some vectors. So if your w is a span of some vectors, to find w perp, we just need to find the vectors such that the dot product with this w1 and the dot product with this w2 has to be 0. In other words, we are looking for the vector u that is orthogonal to w1, okay, to w1, and you're looking for vectors that is orthogonal with w2, and this will be enough to figure out what is the orthogonal complement of this vector space W. And according to our computations, it's no surprise to see that your W perp is going to be the span of your k vectors, your ij, k, or k vectors. All right, remember in our example right here, right, W is the xy plane actually, and so W perp turns out will be this vectors right here. Okay, it's going to be I mean, not this vectors, but it's going to be on this line. Okay, this is going to be right. Okay, I can draw it here, not a problem. All right, so that is going to be your W perp. Okay, so that's going to be your W perp. So we can summarize these observations here and write as a theorem, right? So we can write as a theorem. This is a theorem I am talking about, right? So if you have a vector space W, this vector space W either has 0 vectors, only the 0 vectors in it, or it will have infinitely many elements. So in order to apply our definitions W perp, that's going to be tricky because it's very difficult to find a vector that you know is going to be orthogonal to every single vector in this vector space W. However, if your W is the span of W1, W2, all the way to WK, in order to compute W perp, you just have to find all the vectors that is orthogonal to this vector, and then to this vector, and then to this vector. So all the way, you just need to find a vector that is orthogonal to k of this vector and not infinitely many of them. That will be enough for you to find W perp. Okay? All right. So let me give you one analogy, okay? All right, so the analogy is this. So suppose we have infinitely many clones, for example, just like in Star Wars, you have clone army. So if you have a disease that can kill off this particular, I call it gene or something, and kill off all this, kill off in the sense that the dot products is equal to 0. And because every element is written as a linear combination of this, so just by killing off all this K gene or something, you will basically wipe out this entire W, okay? So every element in W will be killed just because they are written as a combination of the individual component where all those individual components are susceptible to this particular disease. So that's explained why. So sometimes when you have a clone and if it is susceptible to one particular virus or bacteria or disease, then the whole species will be gone. And that's the reason why it's very important to have diversity in terms of their gene pool. So that, like, for example, in human race, and if there is infections, there's a disease, it's very unlikely they will wipe everybody out because some of them will be immune and will survive. And that is the analogy. I mean, like, not very closely related, but you can think of it this way so that it helps you in remembering that this important facts, okay? All right, now, the next thing we want to talk about, it is time to talk about stuff like this because we haven't been talking about checking subspaces for weeks now. So this is a good time to practice how do you verify something is a subspace of something, all right? So this is a theorem that claims that if W is a subspace of Rn, all right, then W perp originally just defined as a set, okay? Now, this W perp, this set here, according to this theorem, is also a subspace. So this is also a subspace, hence a vector space of Rn. Okay, so if W is a subspace of Rn, W perp is actually also a subspace of Rn. All right, so how do we verify a set is a subspace of something, right? So it's been a while that we haven't really do this particular exercise, so this is a good time to review that. So if you want to show that W perp is a subspace of Rn, number one, you have to show that it is non-empty, and we already established that. Okay, we have one element that is in it that's non-empty. The next thing you need to do is to show that W perp is closed under additions. That means you take two elements, right? You take two elements. Let's say you take vector U and vector v that is in W perp, and you want to show that the sum is also in W perp. That's called closure under addition. So this is not very difficult to do. So you know that u in W perp means this, right? U dot W is equal to 0 for all the W in W. V is W perps implies that V dot W equal to 0 for all the W in W. So now you look at what happens if you look at the U plus V and see whether they are orthogonal to every element that is in W. And you can see that the answer is yes. Therefore, that U plus V is also in W perp. Given that U is in W perp, V is in W perp, U plus V now is also in W perp, and this is enough to show that we have closure under addition. So closure under scalar multiplications is not something that is very difficult to do, and you can see this is how you do it, and therefore because W perp is closed under additions and closed under scalar multiplication, so W perp is a subspace of Rn. All right, not very difficult, and it's a good time to review that particular techniques. All right. Okay, so now we are going to show you another property of W and W perp. So let me draw you the picture again. So you're in Rn. So you have W, which is a subspace of Rn. So this is given. This is a subspace of Rn. And let's say we compute W perp. Okay, let's compute W perp. We found them. And from the previous theorem, we know that W perp is not only a set now, this is also a subspace of Rn. And what this theorem is trying to tell you is that if they ever intersect, okay, this intersection here between W and W perp contain exactly one element, and that element is the zero vectors. That's the only element that is common to W and W perp. So how do we prove that? Now, recall that if you have a set A and you have a set B, so these are all sets, in order to show that these two sets are the same, so we will have to show that one of them, okay, is a subset of the other, and the other one is also a subset of the other, okay, of A, right? So we have to show two directions. A is a subset of B. That means every element in A will be also in B. And you also have to show that every element in B will also be in A. All right. Now, all right. So this is a set equality because this is a set. This is a set. All right. So how do we actually show that W and W perp, if you look at their intersections, it consists of only one element, which is 0, which is a set of 0. Okay, one of the direction is pretty straightforward. So if you look at W, W is a subspace. So we know from homework, from midterm exam, and from a lot of other different places that you know that if you have a subspace of Rn, that subspace must contain the zero vectors. And W perp, we just show that it is also a vector space, a subspace of Rn. So here we also have a zero vector. So zero vectors is an element that is common to W and also W perp. Zero vector is in W and also in W perp. So therefore, it is in the intersection of W and W perp. So this set, which contain only the zero vectors, is a subset of W intersect W perp. All right, so this is what we call the easy directions. This is very easy to show. The facts follow very easily, just simply knowing that W is a subspace and W perp is a subspace. And just because of that, we have this direction. The other direction is a little bit trickier, not too bad, but a little bit trickier. That is to say, we want to show that every single element that is in W and also in W perp must be 0. All right, so that's what we want to show, which means that if you take an element, if you take one element from this set, let's call them A, right, which is in Rn. If you have an element that is in W and also simultaneously in W perp, then this A here has to be the zero vectors. No choice, but have to be zero vectors. Okay, so how do we do that? Not very difficult. Okay, so let's take an element. Okay, let's take an element, just like what I said. which is common to W and W perp. All right, so this A here, okay, remember, is in W and also in W perp. All right, so let's look at what happened if this is in W perp, right? Logics, okay, logics, think about it. If your A is in W and also in W perp, then in particular, your A will be in W perp, okay? Now, think about what does it mean when A is in W perp. If A is in W perp, that means that A dot W has to be equal to 0 for all W that is an element of this vector space W. Okay, let me say that again, right? Okay, let me say that again. A is in W and W perp. A in particular is in W perp, and by definitions, A dot W has to be equal to 0 for all W in W. Now, the key thing to realize is that A is also in W, right? A is also in W. How do you know that? Because we take an element that is in the intersection of these two sets. So in particular, A is in W. So which means that when you go through all the possible W, one of them is actually A. All right, so A dot W has to be equal to 0 for all the W. In particular, A dot A must be equals to 0. How do we know that? Because this one right here is one of the element in W. Now, A dot A equal to 0 means what? One of the property of dot product, if you remember from the video on dot product, A dot A is always non-negative, and A dot A, if it is equals to 0, that means that your vector A has no choice but has to be equal to 0. So we are using it there, and you can see that that implies immediately that if you have an element that is in here, that element cannot be any element except the 0 vectors. Therefore, we have these inclusions. Therefore, we have this sets equality. Okay? All right. So now we know this very interesting facts that W and W perp have one common elements and one common elements only, and that is the 0 vectors. All right, so finally, I want to show you something very important. It is so important, we have a name for that. It's called fundamental theorem of linear algebra. So you might wonder, all right, we have vector space W and we have W perp. When do we actually see something like that? In fact, your row space of A, okay, your row space of a matrix A and the null space of A, they are actually orthogonal complement of each other. Okay, this is, I'm going to write down, it's important. So the row space of A and the null space of A, they actually have a relationship. What is the relationship? The relationship is that they are orthogonal complement of each other, which means that RA perp is equals to the null space of A. And you will also see later on that row space of A is also the null space of A perp. That means that they are orthogonal complement of each other. And this picture kind of gives you that suggestion. This is just a cartoon picture. It doesn't really look like that. We draw them like this because there's a famous professor from MIT. His name is Gilbert Strang, and he draw that in his book and also in his famous YouTube video. So we follow along and draw this, okay? So the row space of A and the null space of A are orthogonal complement of each other. And if you look at the column space, okay, if you look at the column space of A and the null space of A transpose, they are also related, and their relationship is that, again, they are orthogonal complement of each other. So you have CA perp, okay, equals to null space of A transpose, or CA is equals to null space of A transpose perp. And that is a theorem called the fundamental theorem of linear algebra. And we are not going to prove it here. We're going to prove it in the next video. And we will also see how we can actually apply them in the next video. And actually, we're going to use this as one of the key ingredients in our very, very end of the semester when we talk about the least square methods. We're going to use that too. All right, so we're going to stop here, and we are going to continue with the proof of this theorem in the next video. All right, so this concludes the first part of the presentation. And in the second part of the presentation, we'll look at the proof of the fundamental theorem of linear algebra, and we are also going to investigate how we can actually apply it, okay? So see you in the next video. Bye.